I want to apply the methods of stochastic mechanics to fields. Let's see. To relativistic fields. So let me begin with a review of stochastic mechanics. We have a configuration space, and in general that's a manifold M. The set of states, the state space, is the tangent bundle. And a dynamical variable is a possibly time-dependent function on the state space. For Newtonian mechanics, we have a mass tensor on the configuration space, and the notion of kinetic energy. This gives a Riemannian manifold, Riemannian metric on M. And this notation is useful even when the underlying manifold is Euclidean space with a flat metric. It might consist of capital N particles, each with different masses, and then the V upper I is the velocity, and V lower I is momentum with masses in the correct places. Newton's law is F equals ma, and we can write that in terms of equations of motion in this way. Now, the more familiar Lagrangian mechanics, we have a Lagrangian, which is a dynamical variable depending on position and velocity. For an isolated system, it's time independent, so the t doesn't occur. Consider a path, capital X, from the configuration, from time to configuration space with velocity x dot. The action is the integral of the Lagrangian. Hamilton's principle of least action is that I is stationary under variation of path, which gives the Euler-Lagrange equations. Now, basic mechanics I call the intersection of Newtonian and Lagrangian mechanics. The potential energy V is defined to be the Lagrangian by the equation. The Lagrangian is the kinetic energy minus the potential energy. And if we calculate using Newton's law, we find this equation that the force is given as follows. But the force must be a dynamical variable. It must depend only on the configuration and the velocity. It cannot depend on the acceleration. So this means that the quantity, the partial of V with respect to the velocity, must be independent of the velocity, because we take the time derivative of it, and that would lead to the acceleration. In other words, to have the conjunction of Newtonian mechanics and Lagrangian mechanics, Lagrangian must be of a special form, a basic Lagrangian that consists of the kinetic energy minus a scalar function of simply of configuration plus a covector on the, again, depending only on the configuration, inner product with the velocity. So phi is called the scalar potential, and A sub I is the covector potential. Now, Hamilton's principal function is the action given by the integral of the Lagrangian, substituting the path into the Lagrangian. And the second form of the principle of least action is that Hamilton's principal function be stationary when the flow is perturbed by a time-dependent vector field. It leads to the Hamilton-Jacobi equation. And for simplicity, I'm going to assume the covector potential is zero, so that the potential energy is simply the scalar potential phi, and the Hamilton-Jacobi equation takes this form. Now we come to basic stochasticization. The word stochasticization is cacophonous, but it's more precise than saying basic or basic. It's more precise than saying stochastic quantization because everything remains entirely classical here. Also, the phrase stochastic quantization has two quite different meanings. So to stochasticize this, the deterministic mechanics, let W be the Wiener process, also called Brownian motion process, on configuration space. So W is characterized as a stochastic process of mean zero, with the W squared is a constant, which I take to be h bar dt, plus a negligible term, little o of dt. And we postulate that the motion of the configuration is a Markov process governed by the following stochastic differential equation, that the differential rather of the stochastic motion is a forward velocity dt plus the fluctuation term differential of the Wiener process. I call it a forward velocity, but the paths are non-differentiable. It's only an expected or mean forward velocity. So the fluctuations are quite singular. They're order of square root dt, which is enormous compared to dt. And if we took a value larger than h bar, this postulate could be falsified by experiment. I mean, if you had a baseball, you can make two position measurements and classically see what the fluctuation is, and you don't see anything classically. So h bar is the largest value you could take here without it being simply falsifiable. Now try to substitute this Markov process x into Hamilton's principal function, and require that the conditional expectation, E sub t, given the configuration at time t of the action, S, be stationary with respect to variations of the forward velocity. Well, there's a problem because x dot, the velocity in the Lagrangian, doesn't exist. The paths are non-differentiable. So what do? Since the paths are not differentiable, we replace the derivatives in x dot by difference quotients and replace the integral by a Riemann sum. Now there's a singular term whose conditional expectation is zero, so it drops out. And there's another singular term that is a constant, an enormous constant, constant proportional to 1 over dt. But it's a constant independent of the paths, so it drops out when you take the variation. And then you pass to the limit when the Riemann sum becomes an integral. That is, the procedure is first you approximate, then you take the variation, and then you pass to the limit. And the result is the stochastic the stochastic Hamilton principal function, which is given by this equation, where E sub x and t is the expectation conditioned by the process being at x at time t. Now, in addition to the forward velocity, b, there is a backward velocity, which in general is different. The paths are not differentiable after all. The current velocity is their average, and the osmotic velocity is 1/2 their difference. And the osmotic velocity depends only on the probability density, the time-dependent probability density rho. And if we define capital R in this way, we can express U, the osmotic velocity. Then computation leads to these two equations. The first equation is the stochastic Hamilton-Jacobi equation. It differs from it by the terms involving capital R. There is no deterministic analog of the second equation because capital R is 0 when Planck's constant, which is in the diffusion coefficient. Capital R is 0 and H bar is 0. So we have here a pair of coupled nonlinear partial differential equations. And if we make the change of variable, psi equals e to the r plus is, these equations are equivalent to the Schrödinger equation. The Laplacian here is the Laplacian with respect to our Riemann metric, so it has the appropriate mass constants in it. So that's the basic theorem of stochastic mechanics. The derivation I've given is that of Guerra and Morato, but based on the classical action rather than what they call a stochastic action. And this result extends to the general case where there is a covector potential and M is not necessarily flat. And when M is not flat, you automatically get the Pauli-DeWitt term, which is h bar squared over 12 times the scalar curvature of the manifold. It pops right out of this formalism. Now, I spoke about this at this conference 2 years ago, and there are many successes of stochastic mechanics, but also there are problems as a candidate for a realistic physical theory. There can be instantaneous signaling between widely separated, correlated, but dynamically uncoupled systems, which I regard as a very serious problem. That's also true in Bohmian mechanics. And secondly, although the probability distribution of position measurements at a single time are the same for quantum mechanics and stochastic mechanics, because the absolute value of psi squared is simply equal to rho, the probability density of the configuration, measurements at two different times, even when mutually compatible, can differ in the two theories. So these are two major difficulties I find with stochastic mechanics as an acceptable physical theory. And the problem is that stochastic mechanics describes a local Markov process and multidimensional configuration space, which is a mathematical abstraction and not in physical space. So let's attempt to apply the methods of stochastic mechanics to fields. There are two motivations for this. One is the hope that since fields live in physical space-time, non-locality problems may be avoided, and the other is that it may provide useful technical tools in constructive quantum field theory. The strategy is to apply basic quantization to a basic field Lagrangian. So consider a real scalar field, phi, on d-dimensional space-time. I shall discuss the free field of mass, a strictly positive mass mu, and the field with a phi-4 interaction. Choose a space-like hyperplane, Rs, where S, the number of space dimensions, is d minus 1. The configuration space is a set of scalar functions phi on this hyperplane. Now impose a spatial cutoff and a momentum cutoff. That is, you put the system in a box of side lambda and represent the field as a set of harmonic oscillators. That's a device going all the way back to genes, with momentum bounded by kappa. Then we have a system with finite limited degrees of freedom. For the free field, of course, the two limits, lambda tending to infinity and kappa tending to infinity, present no difficulty. But it is unwise to attempt to formulate an interacting field on the same space as the free field, since by Hogg's theorem, an interacting field must have an inequivalent representation of the canonical commutation relations. That is, the strategy should be to put the cutoffs in, then apply the interaction, do whatever is necessary, if possible, to make sense of it, then pass to the limit. As Donald Knuth said once, a premature optimization is sometimes an error. So you don't pass to the limit the way you do for the free field. Now, formally, the phi-4 theory has the interaction that's simply the integral over the hyperplane of phi to the fourth dx. With our cutoffs, the integral becomes just a sum, but the expression is hopelessly singular as the momentum cutoff is removed, and the Hamilton is replaced by this Hamiltonian, where the colons denote Wick ordering, which can be expressed very simply in probabilistic terms, simply by summing over quadruples of distinct oscillators. Now, for d equals 2 space-time dimensions, it was shown that the Hamiltonian is bounded below by a constant independent of kappa, giving the limit as kappa tends to infinity. This was the origin of hypercontractivity, which has grown into a rich topic in analysis. The construction of the limit lambda tending to infinity, letting the box grow, followed, in fact, with phi 4 replaced by any polynomial of even degree. For 3 space-time dimensions, the phi 4 theory was rigorously established by Glimm and Jaffe with mass and coupling constant renormalization by heroic work with cluster expansions. Now, these are essentially the only quantum fields that have been constructed with all mathematical rigor. For d strictly greater than 4, Eisenman established a no-go theorem that the limiting theory with cutoffs removed is non-interacting. For the interesting case of phi equals 4, there are partial no-go results, and most workers in constructive quantum field theory believe that the limiting theory with cutoffs removed is free, is non-interacting, also for dimension equals 4, but there's no complete proof. The problem is open. Personally, I expect a positive solution, and it should be related to the Higgs boson. I don't know much about it, the Higgs boson, except that the scalar phi 4 is a part of the description of it. Now, in this work in constructive quantum field theory, Minkowski space was replaced by Euclidean space, giving a problem in probability theory. The Euclidean fields commute. So that's the analog of studying the Schrödinger equation with a potential by studying the corresponding heat equation. And then the relativistic theory was reconstructed for the Euclidean theory. This is a powerful analytic technique, but it does not give a candidate for quantum theory as emerging from an underlying classical theory. Except that I heard or read somewhere that Stephen Hawking is reputed to have said something like the world is Euclidean but appears relativistic. I don't have a reference for this or know what he meant if he did say something like this. So what does stochastic mechanics say? We have a basic Lagrangian, but the separation of the energy of the free field, for the free field, into kinetic energy and potential energy is not a relativistically invariant procedure. Probability theory and relativity do not mix easily due to the indefinite nature of the Minkowski metric. For the ground state of the free field, the corresponding random field of stochastic mechanics was constructed by Guerra and Ruggiero. It is the Gaussian field with the Euclidean invariant covariance function. But it plays a different role than in Euclidean field. Relativistic effects persist. Suppose we have a bounded region, omega, that's bounded below by time t1 and by t2, and we put an external potential in that region that interacts with the free field. Then considering the Markov process, not necessarily for the ground state at free field at time t1, it interacts with the external potential. And then you look at it at time t by the basic theory of stochastic mechanics that gives the correct probability distribution. Since the quantum field is relativistic, the influence of the external potential affects only the points at time t2 that lie in the future cone of some point where the external potential is put. But we cannot conclude a similar result for the Markov process itself. Superluminal influences persist, alas. The situation is that the means are relativistic and the correlations are non-relativistic. The abstract I submitted to this conference several weeks ago was overly optimistic, but let me conclude on a positive note. In my doctor's office, there's a cartoon on the wall. It shows a frog that's about to be swallowed by a stork, but the frog has its front legs extended and is grasping the stork's neck so it won't be swallowed, and the caption of the cartoon is, "Never give up." So let me go back to page 7 here. Well, I'll do it slowly. It seems to be stuck. Okay, too fast. Here we go. It's not correct to say that stochastic mechanics is based on the Wiener process, on the Brownian motion process. It's based on the differential of the Wiener process, which is white noise. And white noise can be formulated in several dimensions. Formally, it's the process with mean zero, whose covariance function is a constant times the delta function. Mathematically, it's simply the Gaussian random field of mean zero indexed by measurable sets where the correlation function is the Lebesgue measure of the intersection of those two sets. This is relativistically invariant. In fact, it's invariant under any measure-preserving transformation. So the white noise is relativistically invariant. Action is a relativistic notion. So there is hope that a relativistic theory with free and interacting fields too can be constructed, which is purely classical fields, random variables, giving the same predictions as quantum field theory. Thank you.
Thank you very much, in particular for staying perfectly in time. So we have actually time for 2 questions, let's say. Are there questions? Andre.
Edward, did I understand correctly that your project that you try to realize stochastic quantization of fields, it is not equivalent to constructive quantum field theory? So it would not be the same, because it's looked because of Feynman-Katz formula, you should move from your project to the existing constructive quantum field theory. I'm wrong.
It can be regarded as giving the same predictions as quantum field theory at a big cost, namely choosing a particular frame, and that's absurd if there's no gravity present. So you'd have to choose and give up locality. So I regard that as quite unacceptable as a theory to explain quantum field theory as emergent. So the straightforward application of stochastic mechanics by insisting on the division between kinetic energy and potential energy does not work satisfactorily.
Another question?
Is your stochastic extension into field theory somehow overlapping with Paris-Yvou stochastic quantum field theory?
I'm sorry, could you repeat that?
If your extension into stochastic quantum field theory is somehow reminiscent or overlap with Paris-Yvou stochastic quantum.
I think it's different, yeah.
Completely different.
It is. That's what I meant when I said there are 2 different meanings of stochastic quantization, quite different.
Just a remark, you don't have to be too much concerned about the cutoff in d equals 4 because it's logarithmic. So if your coupling constant is 1 over 100, then only at energies e to the 100, something terrible happens. It's the Landau ghost. And Furthermore, well, as for the Higgs particle, the reason why the coupling remains small is that it's coupled to a gauge theory, and so
I know it's only
the
part of it.
general theory, suspicion, although not without proof today, is that if you have non-abelian theories added to it, then the cutoff problem can basically be removed. The theories can then be asymptotically free, which is really what you want.
Certainly.
But even if the theory is not asymptotically free, you could say, well, let's keep the coupling small, and then the problems will be so far in the ultraviolet that nobody's going to be concerned about it. You just take your lattice and continue and forget about the divergence problem at the very far ultraviolet.
The general experience seems to be a logarithmic infinity is almost finite.
That's right.